let's review the strong, the logically strong, the good, the valid patterns of inference. In the book, Feldman refers to them as well-formed arguments. And let's take a look at the first pair. All A's are B's. X is an A, therefore X is a B. All men are mortal. Socrates is a man, therefore Socrates is mortal. Analogous kind of inference. It's modus ponens, or affirming the antecedent. If P, then Q. P, therefore Q. If Socrates is a man, then Socrates is mortal. Socrates is a man, therefore Socrates is mortal. Or if you want, if President Obama is in the White House, then he's in Washington, D.C. President Obama is in the White House, therefore President Obama is in Washington, D.C. Next inference, set of inferences. All A's are B. X is not a B, therefore X is not an A. All A's are B's. Everything on the left is on the right. X is not a B. We're going in the not the opposite direction from right to left. X is not a B, therefore X is not an A. All desserts are sweet. Lima beans are not sweet, therefore lima beans are not a dessert. The analogous inference with if-thens, with conditionals. If P, then Q, not Q, therefore not P. If lima beans are a dessert, then they are sweet, or then lima beans are sweet. Lima beans are not sweet, therefore lima beans are not a dessert. Modus tollens, or denying the consequent. The final inference. All A's are B's. All B's are C's, therefore all A's are C's. All dogs are mammals. All mammals are animals, therefore all dogs are animals. And we have on the if-then side, the conditional side, hypothetical syllogism. Remember, hypothetical is another name for a conditional. If P, then Q. If Q, then R. Therefore, if P, then R. If that is a dog, then it is a mammal. If it is a mammal, then it's an animal. Therefore, if it is a dog, then it is an animal. Okay, we're going to move on now, having reviewed that, to a couple of final inferences that we're going to spend a little time on. And we're going to take a look at the relationship between, how do we make kind of a negation, or how do we flip around the if-then, if P, then Q, if we want to have something with a Q first and a P from that, how are we going to get that? So if we take a look, if P, then Q, in the first case, P is Q, true, Q is true. If P, then Q is also true. Now in that case, not Q would be the opposite of what Q is, which would be false. Second case, not Q, Q is false, not Q is true. Third case, Q is true, not Q is false. Fourth case, Q is false, therefore not Q is true. Now let's see where not P comes in on this. If P is true, the first line, not P is false, P is true, not same thing there. The third line, third and fourth, P is false, not P is true. Now let's take a look at the conditional, if not P, then not Q. Okay, if the first one, then the second one. And remember, the only case in which a conditional is false is when the antecedent, in this case not Q, is true, and the consequent, not P, is false. In other words, the second case, that is the only case in which that conditional is false. So all of the rest of them are true. But notice something interesting. What this tells us is if P then Q has the same truth value as if not Q then not P. It's kind of, if you think about modus tollens a little, that's the way you get the right side, the consequent, in the antecedent. You have to put a not, a negation in front of both of them. And what that suggests is a new form of inference known as contraposition. So if P then Q is true, therefore if not P then not Q, or going the other way, if not Q then not P, therefore if P then Q. We know that those two are the same, logically equivalent. That is, the premise and the conclusion are logically equivalent, have the same truth value, so we can conclude one from another. Now, the next thing we want to look at is the biconditional. And what the biconditional says is P if and only if Q. So it says P is true if and only if Q is true. In other words, if P is true, then Q is true, and if Q is true, then P is true. We see they have to have the same truth value, P and Q in this case. So where they do have the same truth value is when P and Q are both true or both false, which is our first line and our last line, and the equivalence being P if and only if Q, that's true. Therefore, P, is the second premise. Okay, so P has to be true. Where is it? We're just down to the first case. Therefore, Q is true. So that is an inference called equivalence. And we see from that truth table why that one actually works. That is a valid pattern of argument, a valid logical form. It's a logically strong argument. It is a well-formed argument. Just want to mention two variations of another pattern known as a dilemma. You guys may know what a dilemma is. That is, a dilemma is when you have a choice between two things. Usually in English it's both are not happy choices. That's not necessarily the case here, that they're not happy choices, but it tells us something about the logic and the inferences. There are two variations in this. We start with P or Q. Either P or Q is true. If P is true, then some other thing follows R. And let's say if Q is true, then S follows. So either R is true or S is true. Another variation is the following. P or Q is true. If P then R, that is, P implies something. Q, if P then R, Q implies R also. So either P or Q. P implies R, Q implies R, therefore R. We can think of something, let's say we're driving down the Belt Parkway and we're approaching the exit for the Verrazano Bridge. Either we get on the Verrazano Bridge or we continue on excuse me, to towards Manhattan. If we get off for the exit for the Verrazano Bridge, then we're no longer in Bensonhurst. And if we stay on, we end up going through Bay Ridge and some other neighborhoods, then we're no longer in Bensonhurst. Therefore, we're no longer in Bensonhurst either way.